A piston cylinder device contains 3 kg of saturated water vapor at 200 kilopascal. Now heat is transferred to the system at constant pressure until the temperature reaches 200 degrees Celsius. Calculate the work done by the steam during this process. So this is a piston cylinder device. We can start with sketching our system. Now we should start writing down what is given to us. So they tell us the mass is 3 kilogram and it is a saturated vapor initially of water, and the pressure is 200 kilopascal. Now heat is transferred. Okay, so let's sketch that too. Heat is getting in. This is happening at a constant pressure, and when heat is transferred, there must be some work done, and that work is the boundary work, because probably the piston is pushed towards upward with the addition of heat energy to the system, and there must be some expansion. Okay, so this is the boundary work. So they're asking for the boundary work done by our system, which is steam, water steam. So what else they are giving us? Let's see the temperature at the second state. I would write it down so we can see the clear picture. Now, since they're asking for the boundary work, you can either find it from energy balance, or you can find it from the equation we learned for the boundary work, which is PDV work, right? Now, since in the energy balance there will be additional types of energy interactions like heat in addition to work, there will be too many unknowns that I cannot just solve it for boundary work, because they don't give me any value for the heat interaction. So I would go ahead and try to solve it using this relation for boundary work. Since it's a constant pressure process, that means that initial pressure is equal to the second state pressure, and there is a constant pressure during the process. That means when we are taking that integral, it can easily get out of the integral since it's a constant throughout. So that is something good that we can use. And we now, if we do that, actually, let's see how it's gonna look like. And we can also say we can represent the volumes in terms of mass times specific volume, and we can write it like this. That means since we know the pressure, we know the mass, we need to know specific volumes at the first and the second state to be able to basically calculate boundary work from this equation. Therefore, now the question is, how can I figure out the specific volumes? And specific volumes are intensive properties of our system, which is water. And we can look at the tables to read the properties of our system. So therefore, probably we will look at the tables. But the question is which tables we need to look at. So the first one is, if we analyze the first state, let's write it down. If we analyze the first state, we are given the pressure and we are also given the information that we have saturated vapor. So together this information should be enough for me to look at the right table to read the specific volume. So we go to water tables, table A5, and find our pressure, which is 200 kilopascal. And now we can read saturated water vapor specific volume here. So this is our specific volume. Now we can record it, going back to our notes. Okay, very good. The next thing is for the second state. For the second state, what is the specific volume? Let's analyze the second state. We know the pressure. And the question is, what else we know? Let's take a look at. So in this question, they don't give us any other property that you can directly look at your tables, but they give you a hint. Okay, they tell you it's a steam. So that means that it is okay to assume as it is steam, but still I would be careful. Actually, looking at the things we have written for what is given for the second state, now I notice they actually gave us the temperature. So in addition to the pressure, they actually also give you the temperature. So this should help. Let's go to tables, temperature tables, or pressure tables, that's fine. At 200 pressure, kilopascal, this is our saturation temperature. So if we look at it, the saturation temperature at 200 kilopascal is 120.21 degrees Celsius. What does that mean? That means that we already passed that temperature because your temperature is 200, which is bigger than the saturation temperature. And therefore, what that means is you have superheated vapor. So we actually confirmed what the problem statement was already trying to say. Okay, so with that information, we now need to look at superheated tables. Table A6, 4.2 megapascal, right there. At 200 degrees Celsius, what is the specific volume? Is 1.08049. We go back and write it down. Very good. Now we already have what we need to solve this problem. So because the boundary work was the pressure is 200 kilopascal. We write it down. We also need mass. Mass is 3 kilogram. Now the specific volume difference. This, if you do this correctly, it should give you the boundary work to be 117 kilojoule. An insulated piston cylinder device contains 4 liters of saturated liquid water at a constant pressure of 175 kilopascal. Water is stirred by a paddle wheel while a current of 7 ampere flows for 45 minutes through a resistor placed in the water. If half of the liquid is evaporated during this constant pressure process, and the paddle wheel work amounts to 300 kilojoules, determine the voltage of the source. Okay, so first of all, understanding this is a piston cylinder device, a closed system that the volume can change, and energy interactions are electric work, shaft work, and also you need to identify there has to be some boundary work there. And it says half of the liquid is evaporated, so that means there is some expansion in the system due to evaporation, and throughout it's a constant pressure process, and they're asking for the voltage of the source. The only way to find the voltage of the source is to find electric work. And to find electric work, you need to write energy interactions, energy balance. And there is no other way. You need to write down very clearly the energy balance, and from the energy balance, you need to solve it for electric work, and then from electric work, you need to find the voltage of the source. So let's write it down. Always for a closed system, the energy balance, we write energy getting in minus energy getting out is equal to the change in the internal energy of our system. Now we write more explicitly which energies are getting in. We see that electric work is getting in plus shaft is getting in. And here, in addition to electric and work, we also see electric work and shaft work. We also see there's a boundary work getting out. And this should be equal to internal energy change. Now, in the problem statements, in many places, they try to tell you that this is a constant pressure process. That means if you remember, for a constant pressure process, it is possible to combine internal energy change with the boundary work and represent them as a single property change, which is enthalpy change. We can do that since it is a constant pressure process. So this simplifies our energy balance to electric work plus shaft work is equal to delta U plus boundary work, which becomes enthalpy change. Now, I'm sorry, this is not very clearly written. So once you figure that out, now you look at your equation. This one we are trying to figure out. This one is given. This one probably I can calculate. How? because I know this is mass times H2 minus H1. Very good. That means there must be a way that I calculate the mass enthalpies at the first and the second state. And how we can do that is we probably need to look at the tables. Since they gave me the volume, I can use the volume and divide it to specific volume and at the initial state and figure out the mass. And enthalpies are some properties of our system that we can read from the tables. Now let's analyze the first state and what we can read from the tables for that. So for first state, they tell us it is what they're giving us. Let's write it down. First of all, they say 4 liters of saturated liquid water. So they give us saturated liquid. They also tell us the volume. But volume itself is not a property we can use to look at the tables. What else they tell us is the pressure. Very good. So we know the pressure and we know it's a saturated liquid. Those informations enough for us to be able to look at the tables. Now at 175 kilopascal we find for water. Let's take a look at it. Let's erase that. 175 kilopascal. And what is, we have a saturated liquid. Saturated liquid specific volume is this. And saturated liquid enthalpy is this one. Let's write it down. Okay, now next thing is you might realize that you have to calculate the mass, and you can do it because they give you the mass and the specific volume is something we figured out from the tables, and we can use this relation to figure out what is the mass. So 3.784 kilogram is our mass. Now, what else we need to calculate, or what else we need to look at the tables for? This one we figured out, this one is done. We need to figure out H2. Let's analyze the second state. What do we know about the second state? First of all, we know that the pressure is a constant pressure process. So we know the pressure. Second thing we know is that they tell us half of the liquid is evaporated. So that means that you will have to have a mixture, therefore. So you actually know that you have a mixture. So what you can do now, use the equations to calculate the enthalpy through quality, which is this equation. By telling you half of the liquid is evaporated, they're actually telling you the quality. Actually, we can write it there. 0.5. Well, we look at the same tables at that same pressure. Here is HF and here is HFG. All right, so all we have to do now is plug those into our equation and calculate H2. I hope I might not have a space there. Let's start from here. You can put the units, don't forget the units. So H2 should be 1593.6 kilojoule per kilogram. Very good. Now we have everything we need and we can use those to calculate the electric work. So remembering our energy balance, right? We need to write down the shaft work. Shaft work is 200, I think, let me check, 300 kilojoule. And we need to find electric work, which is equal to mass times H2 minus H1. If you solve this equation correctly, you will find electric work, which is the voltage times current times the time, is equal to 3887.34 kilojoule. And since they already gave us information about the current and the time, let's use it. So voltage times current is 7 times time is, I think, let's check, 45 minutes. And 1 minute is 60 seconds. Now I need to use another unity conversion ratio here because I need to get rid of the voltage and ampere. Instead, I need to use kilojoules as energy unit. Okay. So what we are gonna do is 1 kilojoule per second is 1000 voltage times. This unity conversion ratio, you don't forget, is equal to this. And from here, you can calculate, right, what is the voltage. And you should calculate it to be 205.86. This is your final answer here. One kilogram of water, initially 90 degrees Celsius with a quality of 10%, occupies a spring-loaded piston cylinder device. At this state, a linear spring is touching the piston, exerting no force on it. The device is heated to compress the spring until the pressure rises to 800 kilopascal and the temperature is 250. Determine the total work produced during this process. So what do they mean is find the boundary work when the boundary moves, meaning the piston in the piston cylinder device moves. So what do they give it to us is first state conditions and second state conditions, and we need to calculate the boundary work. And one way to do it is work with the PV diagram, and if we can plot the behavior of the pressure changing with the volume, and in the graph, in the diagram, we can calculate it by looking at the area under the diagram. So what we need to do is now let's analyze what they're giving us, and let's see if we can plot the PV diagram. So here mass is 1 kilogram. We are dealing with water. And what are they giving to us is initially temperature is 90 degrees Celsius, and they're also giving us the quality at the first state. It's 10%, means 0.1 quality, and the pressure at the second state and the temperature at the second state. Now, to sketch the PV diagram, I need to know the pressures at first and second state, and I need to know the volumes at first and second state. And how can we do that? Of course, we need to look at the tables. So when we analyze state 1, we are given that we have a mixture. It has a certain quality and temperature. So if you have a mixture, that means basically at that temperature, you have to be at the saturation pressure. So we look at the tables for water for 90 degrees Celsius. 70.183 kilopascal should be our pressure. This is because we have a mixture at that temperature. And only way you can have a mixture is if you are at the saturation pressure at that temperature. So now we know the pressure at first state, we know the pressure at the second state. Let's see now at the second state, what would be the volumes, and at the first state, what would be the volume, because now we need to calculate the volumes, right? Because our goal is essentially be able to plot PV diagram so that we can find from the area underneath it what is the boundary work. Now the keyword is here, the question tells us linear. So they are telling us a linear spring is a way to tell us that there is a change and the change is linear. And then we can understand this is a linear change that's going to happen from state 1 to 2. But for now, we just know the pressures for the y-axis, but we also need to know the volumes or specific volumes. First, of course, then the volumes for the x-axis. So first now look at the state 1. For state 1, we have a mixture. So if I want to calculate the specific volume, I need to use the quality. For VFG, we can say VG minus VF. Now VG, VF, we can read from the tables, exactly the same table. We can read those. and we can plug those in and calculate. Let's remember what the values were. Okay, and then we can just plug it and in and then calculate what is the specific volume. So this is VF is 0.001036 plus, you can put the units, and quality is 0.1, and VG is this that I remember, and VF is again this one. And when we finalize our calculation, specific volume at the first state should be this. Very good. The next thing is now we need to find specific volume at the second state. And for the second state, we know the pressure and the temperature. So you can either start with the pressure tables or the temperature tables. Both will tell you the same conclusion. I would start with the pressure table because that is what is easiest to me to compare the saturation temperature to the temperature that I have. Is easy for me. So I'm just gonna look at 800 kilopascal if we have that table. 800 kilopascal, temperature for saturation temperature is 170.41. But our temperature is 250, which is way above that. So the boiling already started and now we have superheated at that temperature. So I can conclude that I have superheated water. Now the next thing is of course going to the correct tables then. And the correct tables are listed. Table A6 for superheated. And we need to find the pressure we have. The pressure we have was 0.8 megapascal. Let's find it right there. And at 0.8 megapascal, we are trying to read the specific volume. We were also given the temperature. Temperature was at the second state. It was 250, so I locate that here and then come in the correct line. And then we can read the specific volume to be basically 0.29321 meter cube per kilogram. Let's write it down. Very good. Now we need to calculate the actual volume, total volume from using the mass. Mass is given to us and it was 1 kilogram. Oh, so basically we just need to multiply with 1 and this will make it and then same for the second volume. Now the next thing is creating the PV diagram, and let's get this one. And this. Initially the volume was 0.23688. Excellent. and then the volume increased to 0.29321, and the pressure was, we have calculated or looked from the table, 70.183 kilopascal right there. This is our first state. And then second state, we have the pressure of 800 kilopascal. So this is the second state, right? So let's use other colors so we can clearly see. And the change is linear because it's a linear spring. Okay, that's the boundary work. So we just need to find the area underneath this, which is a trapezoid, and we can calculate it from there. So for the trapezoid area, we know that we need to sum up this with 800 over 2 times the volume change, which is, actually we can calculate it somewhere else. And then we're just gonna multiply this with that. And then boundary work should be 24.5 kilojoules. A piston cylinder device initially contains 0.3 kilogram of nitrogen gas at 160 kilopascal and 140 degrees Celsius. So we have a piston cylinder device. Initially the mass doesn't change because it's a closed system, but the mass is given to be 0.3 kilogram, and then the pressure is 160 kilopascal. Actually, wait a second. Zoom in a little bit. And it is important to write down clearly what is given, not to make any mistakes. For any question, I would always do that. The nitrogen is now expanded isothermally. Oh, so that means temperature doesn't change. And to a pressure of 100 kilopascal, the pressure is though changing. Okay. Determine the boundary work done during this process. So there are several ways here, right? We can use our calculation, which is integrate PdV. And then also another option is if you can graph PV diagram, and you can do that. But for that, you need to have certain information, and you need to know if there's a linear change or not. Because if there's no linear change, and if the problem statement doesn't give us any information about that, it is very difficult to calculate the area underneath the PV diagram, because it's not going to be a simple geometric shape. So let's see. If I notice this is an ideal gas, which is that I know how P depends on V, and I can take the integral for PdV. So if you remember how we calculate the boundary work is, of course, to take this integral, we need to know how pressure depends on the volume, so we can take the integral. But we know it here because we know ideal gas equation applies to nitrogen gas. So remember, PV is equal to MRT. Okay, so what we can do is then several things we can do, right? Let's work with the ideal gas equation now, and which is, again, I'm sorry, I need to write very clearly for myself so you guys can understand better. So this ideal gas law applies to first and the second state. You can write P1 V1 MR T1. Remember, MR doesn't change. It's a closed system. Mass doesn't change. R doesn't change. And you can apply it to second state. And we know T1 is also equal to T2. And we can say they are both equal to T naught, which is a constant. And what we can do is basically solve this ideal gas equation for the knowing the function of the pressure, how it depends on the volume. And we know that how it depends on volume, right? If we look at it, pressure is equal to mRT over V. So I can plug this in to my integral. Since mRT naught is a constant, it gets out of the integral. And we have mRT naught ln V2 over V1. Okay, so since they don't they actually tell us the mass R, we can find it, and actually they also tell us T naught, which is 140, but remember to use Kelvin in the ideal gas equation. They also give us the volumes. I mean, they don't directly give us, but it is something you can calculate from ideal gas equations. And also you can remember from what we learned in the classroom. Let's repeat it here also. You can replace V2 over V1 with P1 over P2, because we know that P1 V1 over RT1 is equal to okay, and then these are same, and that means P1 over P2 is equal to V2 over V1. So there's an opportunity where if we don't know the volumes, we can replace them with pressures. And in here, actually, you know the pressures. Actually, you can do that way, right? So one way to solve this is, therefore, what we can do is mRT naught ln, replace that V2 over V1 with P1 over P2. There is also a way from each ideal gas law for each state. You can actually also calculate the volumes. You can do that. But since they already give me the pressures, like I don't have to go through that, and they give me the mass. So let's plug in. So the mass is therefore 0.3 kilogram. R is something, remember, we need to go to table A1 for nitrogen gas. We need to read it from there. Let's see. It's right there. So we come back and we write it down. and temperature should be in Kelvin. And we need to continue here, multiply this with ln P1 over P2. P1 is given to us and it was 160 kilopascal. And P2 is given 100. So if you do that, you should get, if you do it correctly, the boundary work is 17.5 kilojoules. Nitrogen at 100 kilopascal and 25 degrees Celsius in a rigid vessel is heated until the pressure is 300. Okay, so when I see that, first I notice nitrogen is an ideal gas. I can use ideal gas equations to figure out the properties of my system, and then they give me the pressure at the initial state. They give me the temperature. And then they also talk about the rigid vessel. So I understand from that statement that the volume doesn't change. Specific volume doesn't change either because the mass is the same. So, and they also tell us pressure becomes 300 at the second state. Now calculate the work and heat. So, well, they're not giving us any information about work. And in a rigid tank, like boundary doesn't move. And without knowing any information, what type of work they are talking about, and knowing the boundary work is not there, and I would say directly work is 0. Because there is no boundary work here. It's a rigid tank. Now the next is they're asking the heat transferred during this process. Okay, if there's a heat transfer during this process, and if we need to figure that out, that means we have to write energy balance because heat exists in the energy balance. So therefore, we know how do we write energy balance. Energy getting in minus energy getting out is equal to the change in the energy of the system. From problem statement, we understand that there's only energy getting in, which is heat, and that is changing the internal energy of the system. And now when we are dealing with an ideal gas other than air, if it's nitrogen, instead of delta U, what I can do is write down mass times CV average times delta T. And delta T being, of course, T2 minus T1. Now let's take a look at it. We know T1, but we don't know T2. And the problem hints us saying use the room temperature for specific heat. So it actually guides us to this approach, right? They are telling us to use the specific heat for nitrogen. So we need to figure that out. So what does that mean is at 25 degrees Celsius, we are at room temperature. Even though we don't know the second temperature, which can help us to average the temperatures, but we don't know it, the problem tells us you don't have to worry about it, just take the CV at that room temperature. That's fine, we can read that. Where can we read that? From table A to B. For nitrogen, it's the room temperature, and therefore 0.743. Looking at it, seems like you don't know the mass either, but they're telling us that we don't actually have to calculate it, because they're asking you need to find the heat in terms of kilojoules per kilogram. Well, if they just asked in terms of kilojoule, we could have find the mass from ideal gas law. That is fine. But here what we can do is we can just basically eliminate mass from our energy balance. We can say, since Q in is equal to if I divide each term to mass, this becomes lowercase q energy transfer per unit mass is equal to CV average T2 minus T1. That is exactly what they're asking for. They're asking for this because they're saying in kilojoules per kilogram. So they're asking for energy transfer per unit mass, which helped us to get rid of the mass from our equation. Great, now we also read this value of the specific heat from the table, but we don't know the temperature T2. So what can we do to calculate the heat transfer? We of course then need to know the value of T2. Since that's a property of our system, I would think about if I can actually use the ideal gas law here. So let's write down ideal gas law, ideal gas equation of state for the first state and second state and see where it guides us. So P1V1 is equal to MRT1 and P2V2 is MRT2. Now we know since for sure M and R is the same for a closed system, we can say P1V1 over T1 is to be equal to P2V2 over T2. Now we also know that this is a rigid tank, so this cancels out. And now what happened is P1 over T1 is equal to P2 over T2. If there's, I made a mistake there. If there's a chance where I know everything except the T2 here, then I should be able to calculate T2. Let's look at it. We know pressure 1, pressure 2, T1. That's very good. And that should help me to calculate the second state temperature. So P1 is T1 is P2 is and T2 is something we try to find. Very good, we found it. Now there's an opportunity where you can average the temperatures and read better specific heat value from the tables, but the problem statement tells us you don't need that. You can just look at the room temperature specific heat, and that's what we did as the problem statement told us. Now what we need to do is just plug in the numbers we found into our equation. So in order to find the heat interaction per unit mass, we read what the CV was. And we also know the temperature difference. This tells us this is the value of the heat interaction per unit mass. 442.8. A mass of 1.8 kilogram of air at 120 kilopascal and 34 degrees Celsius is contained in a gas-tight frictionless piston cylinder device. The air is compressed to a pressure of 600, and during this, heat is transferred to the air such that the temperature stays the same. Calculate the work input during this process. So if we have a piston cylinder device and there is a heat interaction, and they're also telling us about what would be the work input. So basically compression, boundary work. Okay, if they're asking for a boundary work, I know a way to calculate it, which is this one. And since this is air, ideal gas, I can replace pressure with MRT, not dV. Okay. And remember last example we did T1 is equal to T2 here, and then T2 is both are equal to the same temperature, which is T0. And this is a possibility where we can also take this integral, which is this is a constant getting out of the integral, and this is like that, just like we did in the problem, I think it was 5. Oh no, problem 4. Okay, so we explained this in detail in problem 4, so you can go to that recording and watch it again how this is possible. And here, since the pressures are given to us, I would just replace this with pressures. Again, go to example 4 to understand why that is. So now all we have to do is basically put in the numbers to calculate the boundary work getting in, or compression. And the result should be negative, because negative means a compression. So the mass is 1.8. R is, let's see what is the gas, air. So again, for air, you need to look at table A1 and read the R. And the temperature in Kelvin, right? What is 37? That is important. You need to add 37 plus 273, which is 307 Kelvin. And ln P1 is 120. They need to be in kilopascal. Okay, so that's simple. We figured it out, minus 255 kilojoule. And the minus sign confirmed that it's compression. Okay, so now we have saturated water at 200 degrees Celsius, expanding at a constant pressure isothermally in a piston cylinder device until its quality is 80%. So it tells me initially we have saturated liquid water. If we look at the PV diagram, initially you have saturated liquid water at 200 and it's expanded at a constant pressure. Volume is increasing at a constant pressure. like this. So that means this is also happening according to the problem statement. It's happening isothermally, so at a constant pressure, at a constant temperature. And this happens until we have a mixture. So at state 1 you had a saturated liquid, at state 2 you have now a mixture, because they are giving you the quality. And determine the total work produced. That seems like just the area under PV diagram, which is just a rectangle. And I think if we know the volumes and the pressures, we can calculate this. So since this is a constant pressure process, we just need to have one value for the pressure, because P1 is equal to P2, and this should be basically the saturation pressure at 200 degrees Celsius, because you have a saturated liquid, and only way to have a saturated liquid at that temperature is when you are at the saturation pressure. It is for water, so I'm just gonna look at the tables for 200 degrees Celsius. So the pressure is 1554.9. Very good. Now this is our pressure, so we can write it. Now we need to find the volumes. The first volume is given, it's 1 meter cube. Okay, but we don't know the second one, and we need to find the second one. So how can we find that? Now we can find it maybe because we can be able to figure out specific volumes at first and second state. So let's do that. So first of all, initially, volume, what specific volume, what could it be? So I know the temperature, I know the pressure, I know it's a saturated liquid water, so this should be equal to VF. So we go back and read this value right there. Let's write it down. Second specific volume at second state, it's a mixture, so you need to use quality to calculate it, which they already give it to us, right? So I just need to plug in everything I know. First of all, we are at the same pressure, there's a mixture now, so we can read the VF and we can read VG and calculate VFG from their difference, and then plug it in here. Let's check again. Correct. Let's now calculate specific volume. At the second state, we need to use quality because it's a mixture. And it is meter cube per kilogram. Very good. Only thing that is left is finding the mass. And actually we can find the mass because at the first state they gave me the volume and they also guided us to find the specific volume. So from the volume and the specific volume, you should be able to figure out the mass, right? And this mass has to be the same as the second state mass because it's a closed system. what I'm trying to say is basically when we are trying to calculate the mass, what do? We do this. Right? Therefore, we can actually be able to find second state volume using this relation, because if you solve it for V2, here you can figure it out that it is actually V1 times V2 over V1. So very good. So this is a relation that we can use to find the second state volume that we were missing. And here we can do that. V1 is 1 meter cube. V2 is this that we figured it out. And then V1 was okay, so this should guide you to the correct volume, which is 88.16 meter cube. Okay, so this is our second state volume. We can write it here. Now you just can calculate here the area underneath this graph, but you can also say basically it is the same thing, is where we have P delta V, which is P V2 minus V1, which is the pressure is a constant volume, and it is that, and the volume change is and then that should tell you what you have, and that should be the boundary work is 1.355 times 10 to the power of 5 kilojoule. A 0.5 meter cube rigid tank contains a refrigerant initially at 160 kilopascal and 40% quality. So initially this was a mixture of refrigerant. Heat is transferred now to the refrigerant until the pressure reaches 700 kilopascal. Determine the mass of the refrigerant, the amount of heat transferred, and also show it in PV diagram. Sure, let's do that. So first of all, we can sketch our system. This is a rigid tank and the volume doesn't change, and heat is transferred our system. That's what the problem statement says. We have a volume of 0.5 meter cube, and we have refrigerant as a pure substance as our system. Initially, this is the pressure, and the quality is 0.4. So we have a mixture first, and then pressure at the second state is 700 kilopascal. Now they're asking find the mass, and then they're asking the amount of heat transferred. So let's figure out what do we have at the first state and second state, and how we can figure out the mass and heat. So first of all, what I would think is, since this is a refrigerant, we cannot use ideal gas equations here, so, or for water either. So to find the mass, probably I will just divide volume to specific volume at the first state or second state, doesn't matter since the mass is the same. And for the heat transfer, I need to use the energy balance. Otherwise, I cannot find an energy interaction. So for PV diagram, to graph that, we need to know what we have at the first state, which is mixture. Now it's becoming a superheated, and this is happening at a constant volume because you have a rigid tank. Okay, so we might be able to sketch it a little bit where we have, let's see if we can do that. So the pressure is increasing at a constant volume, right? Initially it was 160 and it became 700. And that is happening at a constant volume, like this. And with respect to saturation lines, means you need to graph the dome. And initially you have a mixture. So state 1 has to be a mixture, state 2 has to be, what is it has to be? So we don't know. Let's figure that out. So first of all, we have a mixture, okay? And it's state 1. And what we can figure out from that information is we can figure out our properties, like what is the specific volume, what is the other properties if we need that, like internal energy. And let's figure those out. So knowing we have a pressure of 160 kilopascal and a quality of 0.4, you can figure out the rest of the properties. And how can you figure those out is using quality. For example, if you need to figure out the V1, then you need to calculate it through quality, this equation. If you need to figure out the internal energy, specific internal energy, you need to do it through this equation. And which values we can read from the table, UF, UG, UFG, we can read at that pressure. So you come here and find the refrigerant tables, which are table A. I'm sorry, this is gonna be table A. 12, the pressure is 160. At 160, you can read VF, VG, and then UF and UG. And with the quality being 0.4, you should be able to calculate. I'm just gonna give you the exact numbers, what they are, what is the value of V1 and U1. Just plugging in the numbers we have, just read from the table. Please do these yourself by looking at the tables yourself. And if you're able to find the exact values like I am describing here, and if you can do these questions yourself, it is very important because it will tell you how ready you are in your understanding to succeed in the exams. We found specific volume. Do the same thing with U1. I'm just gonna write down the answer. You can do it now. Is 107.19. Okay, so we just have the answers for specific volume, and then the internal energy. As I told you before, it is easy to find the mass once you know the volume and specific volume, because you can use this relation. You can either use this or that, but we don't know right now what is V2. We just know right now. We actually know, because it's a rigid tank, right? And that means V1 is equal to V2, specific volumes too, because the mass doesn't change. So you can use either V1 over V2 or V1 over specific volume, or V2 over specific volume at the second state. Both are valid. You can use both since the mass doesn't change, but I'm just gonna use this one, which we find already, which is actually the same, but and the mass should be this. So if this is our mass, the next thing is we can use that, and they already asking for this value and we found it, but we will also need it in the energy balance, because in the energy balance, remember, heat is getting in and changing the internal energy, and they're asking for that heat interaction. And if you don't know directly that equation in your mind, you can just start from the general form of the energy balance, and notice here is that only energy interaction taking place is the heat that is getting in. So the heat that is getting in is changing the internal energy of the refrigerant. Well, looking at this right now, I'm trying to figure this out. I figured this mass, I know what U1 is, but we forgot to figure out U2. And how can we do that? So we need to know state 2 properties. Looking at it, only thing that is directly given to me is the pressure, which is 700 kilopascal. And it seems like I don't know any other property, but actually you do, because it's a rigid tank. So you need to remember, in the case of a rigid tank, specific volumes are at the first state, and at the second state they are equal to each other. And also the pressure they give us was 700 kilopascal. Now we are trying to figure out what U2 is. So it's a property that we are looking for, and you need to look at the right tables. So how do we understand is, at 700 kilopascal, we are going to compare the specific volume value we have with Vf and Vg. So Vf is this, Vg is that. But our specific volume is 0.049, which is bigger than Vg. That tells me we have a superheated vapor. So we have a superheated. So I need to look at the superheated tables. Let's take a look at it. At that pressure, 0.7. Okay, at 0.7 for refrigerant, they're asking us to find the specific internal energy. For the corresponding specific volume is 0.049. Okay, so I look at this. 0.049 is something outside of what is given as data in the table. So that means you're not going to interpolate, you're going to extrapolate. What does that mean? It's basically similar to interpolation. It's just we need to find the data outside of what is given. So basically, let's read the last two values here for the specific volume and the corresponding internal energy. We go back and write it down. These are what we read. And the internal energy corresponding to that. And then this is also what we can read from the table. And this is our specific volume, right? And we're just gonna calculate the corresponding internal energy. So what we can do here is U2 minus this over is equal to okay, you need to solve this part and then it should give you, okay, let's add a page. Okay, so we find U2 to be this volume. And now from the energy balance, we can calculate the heat interaction. This is our answer. A piston cylinder device with a set of stops initially contains 0.6 kilogram of steam at 1 megapascal and 400 degrees Celsius. The location of the stops corresponds to 40% of the initial volume. Now the steam is cooled and determine the compression work if the final state is 1 megapascal and 250 degrees Celsius and 500 kilopascal. Also determine the temperature at the final state in part B. So we need to remember the problems we have learned when we have a pair of stops. How do we deal with those problems? And here it's talking about a boundary work and a compression work in this case. So they are telling us it was 1 megapascal, 400 degrees Celsius. Then at the second state, it is 1 megapascal and 250 degrees Celsius. So at a constant pressure process, there's a compression. And to figure out that compression, we need to write the boundary work equation, which is PDV. And then we need to calculate it from there, assuming this is the constant pressure process. And basically what they're asking at the part A is which is, since it is a constant pressure process, this is, so we need to know the mass, we know it. We need to know the pressure, we know it. 1 megapascal, it's gonna compress. We don't know where it's gonna stop though right now, okay? So we just know it's gonna be compression at the constant pressure, and we can calculate that compression work If we know the pressure, we know it. If we know the mass, we know it. If we know the specific volumes, and we can know the specific volumes. So because at state 1 we have 1 megapascal and the temperature is 400. We look at the tables and we see that we have, let's see, I previously did this, but let's show it again. So here this is water. They don't exactly say it is water, but they say steam, so I think this is water. That is water steam. What that they mean is they are giving me the pressure to be 1000 kilopascal and the saturation temperature at that pressure is around 180, but our temperature is 400, so we have superheated. Now we need to look at superheated tables at 1 megapascal. At 400, we are reading what is the specific volume. Now we can do the same thing for the second state because we know it's a constant pressure process. The temperature changes to 250, but it's still bigger than the saturation temperature at that pressure. So you have superheated. Again, exactly the same tables we just showed, that you can actually read the specific volume. Now all we have to do is calculate the boundary work. So remember, the negative sign is just because we have compression. So it is work in actually. So therefore, once we figure that out, now what is left is if this goes down, this piston goes down all the way to the pair of stops, how much boundary work we need to do. And we can calculate that also. How? Because we know that the place of pair of stops is 40% of the initial volume. So that means, actually, let's write it down first. That means V2, when it's equal to 0.4 times of V1, is the place for where the stops are located. So if it's gonna go all the way to the stops and stop there, how much boundary work we need for that? How much it has to go down? How much compression needs to be done? So this has to happen at the same pressure, because again, until it freely moves and it's not stopping and resting on a pair of stops, it has to be at the same pressure because they're not adding extra weight on top. It is in balance. The outside forces acting on piston and inside forces, they're in balance. So what we can do here is and we know the value of V1, right? If you plug that in, which is 0.30661, plug it in and you should calculate minus. Yes, so you actually need to go, if you're gonna go down all the way to the pair of stops, then you need to do more compression. So initially it must be stopping somewhere here, and then we calculated the second state properties from there, and now if it needs to go all the way here and rest there, that means it is now, its pressure can change now inside, but it's not gonna crash down. So its pressure can be, for example, 500 kilopascal, like the problem statement says. If it's 500 kilopascal, it has the probability of crashing down, because outside is probably in the same as around 1 megapascal, right, which is about that, and it might crash down the piston, but it cannot because it is resting on the stops. So basically, when they're asking what is the temperature at the final state, assuming it is like when it's 500 kilopascal, you can figure that out from the tables, and knowing that pressure is going to be and then you also know the specific volume, which is 0.4 times of V1. You should be able to look at, let's look at the tables, and 500 kilopascal. And our specific volume is 0.122. Also, it is a mixture. Okay, so if it's a mixture, now what you need to do is first find the quality. No, you don't need to, because all we are asked for a temperature, right? We don't need to calculate other properties. So what we need to do is just look at the saturation temperature at that pressure. That's enough, because they were just asking for a temperature anyways. So it has to be the saturation pressure. Okay. So that's good. That was easy for us to find. Now, there is no more compression work when the pressure is 500 kilopascal, because it has to be resting on the stops, and the piston cannot move anymore, because the pressure is much lower than 1000 kilopascal, and that means it is already all the way down to the piston, the stops, and resting there. Otherwise it would have crashed down. So at 500 kilopascal, there is no more compression work that can be done, and this should be the final temperature at that pressure. Nitrogen at an initial state of 300 Kelvin, 150 kilopascal, and 0.2 meter cubed is compressed with an isothermal process to a final pressure of 800. Determine the work done during this process. So this seems like a simple example, like we did before many times, similar to those where we just need to calculate the boundary work. And there's a piston cylinder device and an ideal gas. We need to use ideal gas equations. So simply instead of P, we write so this is again an isothermal process. So this is okay. So now we don't know the mass. We don't know the mass, and we don't exactly know the volumes either, so I might need to replace that. So remember, P1 V1 is MRT1. I can write it for first state and the second state, but since the temperature is constant, these are both equal to MRT. So I can replace MRT for it P1 V1 or P2 V2, but properties for state 1 is more comprehensively given to us, and then therefore I will just use that. And we also learned in the previous examples, if you go back to our practice examples, this can be replaced with that too for an isothermal process. So what I'm gonna do, replace MRT with P1 V1, and then V over V2 over V1 with P1 over P2. This question is very similar to what we did before many times, so that's simple. Okay, so the helium as a system we have now, the volume of 1 kilogram of helium is 5 meter cubed, and it is compressed to 2 meter cubed, while the pressure remained the same. And determine initial and final temperatures of the gas as well as the work required to compress it. Well, we just need to find the temperatures from ideal gas equation if we can. Let's try. And then the boundary work equation we can use, since this is a constant pressure process, easily to figure out the boundary work. So the first thing is we can write for the first state and then from here what we can do is actually we can use this equation too, right? We know the mass, we know the R, so we know the volume, and we know the pressure. So you can use both here. For example, in this case, you know pressure is 180, and then volume is 5, mass is 1, R from table A1 you can check, and from here you can actually calculate T1 if you want to. And yes, because in other words, anyways, V1 is V1, specific volume 1 is V1 over M. That's the same thing, right, when we plug in here, so it doesn't change anything. But it seems like we are given everything we need to calculate the temperature. So let's solve it for temperature. Temperature is therefore P1 V1 over MR. And let's plug in and let's see how we can calculate that. Initially it is 180. V1 is 5. And the mass is 1 kilogram. And R you read from the table, please. You guys do it. And from here, this is the first temperature. Now the second temperature is, again, remember the relation is P1 V1 is equal to P1 over V1 is equal to P2 V2 over T2. And here the pressures are the same. Therefore, we can cancel this. And what it happens here is V1 over T1 is equal to V2 over T2. Now we know T1, we know V1, and we know V2, and you can calculate T2 from there. Very good. We just know the temperatures now at the first and the second state. What are they? And all we have to do is now calculate the boundary work. Since that is a constant pressure process, we can calculate it from this relation. And the pressure is 180. And the volume change is from so initially it was 5, then it is 2. Compression. And this should give us that's it. A mass of 5 kilograms saturated water vapor at 300 kilopascal is heated at a constant pressure until the temperature reaches 200 degrees Celsius. Calculate the work done by the steam during this process. So what they're giving us is the mass, and it is a saturated vapor at 300 kilopascal at the first state. Now it is changing state at a constant pressure, so pressure doesn't change, and the final temperature is 200. Calculate the work done by the steam during this process. So they're talking about boundary work, and the way to find the boundary work is, of course, using PdV, and that is P delta V, because it's a constant pressure process and P gets out. And with this being said, we know the pressure, but we need to know the volumes. So how can we know the volumes? We need to analyze our system at first state and second state. Initially, it was at 300 kilopascal, a saturated vapor. So we go to water tables at 300 kilopascal, right? Making sure. We read actually this volume, which is Vg, saturated vapor. So it is actually 0.60583. Now we write it down. Okay, and then the next thing is we need to find also V2. We are given the pressure and the temperature. We need to look at the tables. At 300 kilopascal, the saturation temperature is 133.52. which we are at 200, so we are above that. So you have superheated vapor. So we need to look at superheated tables. At the pressure of 0.3 here, and we read at 200 degrees Celsius. This one, 0.71643. All we have to do is then write down our equation, right? We are trying to calculate the boundary work with P delta V, which is mass times specific volume. That's the answer. Okay, so we have saturated liquid water at 200 degrees Celsius, expanded isothermally in a closed system until the quality is 80%. So initially they give us the volume, and we know it's saturated liquid of water, and the temperature is 200. Expanded isothermally, meaning the temperature doesn't change, and expansion means there is boundary work, and at the end quality becomes 0.8. So it's a mixture. Determine the boundary work. Okay, so in a system where we have a piston cylinder device and there's expansion isothermally, so and you are going from a saturated liquid to a mixture, you have to be at a certain temperature and at a certain pressure for this phase change to happen. So it is okay to say that actually the pressure stayed the same because there's a phase change, right? And we need to be at a certain temperature and pressure for this phase change to be taking place. So we have to be at the saturation pressure at that temperature initially. We need to look at tables, and the pressure has to be the saturation pressure at that temperature, because first initially you have a saturated liquid. So with the water tables, at this temperature, this has to be our pressure. Now this is our pressure, and the next thing is in order to calculate this PDV, as I said, the pressure has to be constant because it's a phase change, and we need to also, similar to previous example, find specific volumes here. And the way to find it is, first, initially it was a saturated liquid. So we look at that temperature, what is the saturated liquid volume? This one. Okay, and then the next thing is, as a mixture, how we can calculate V2 is, you know, that through use of quality. And at that temperature, we can again read Vf and Vg. I think there's something missing here. 1 second. Okay. Now, looking back and confirming that it's all correct, and now we can calculate it. Okay, so this is our specific volume at the second state, and now we need to find basically the volumes, and we need a mass for that. And how can we calculate mass? Mass we can calculate from initial state or a second state. But both of them are the same mass because this is a closed system. What we actually know is this one, and this one, and we can figure this one out from this relation. And this should give you, and of course after that we just need to plug this into our equation, which is the pressure is this, and the volume change is this. There is a piston cylinder device contains 0.4 kilogram nitrogen gas at 160 kilopascal and 140 degrees Celsius. The nitrogen is expanded isothermally to a pressure of 100 kilopascal. And what is the boundary work? Okay, this is similar, but in this case we are told that pressure is changing from 160 to 100, and it is isothermal. So when we are trying to calculate the boundary work, we cannot take the pressure out. Instead, we can write MRT over V, which is so after we know this, now we can calculate it. And here the mass is given. R we can find from table A to A. and T is 140, and it's not changing, and we know those. And do we know the volumes? We don't actually know the volumes. Can we replace them by pressures? Yes, we can replace them by pressures, or you can individually work with ideal gas law for each state and then find the volumes. You can find the volumes and do that. But what I would do is, instead of V2 over V1, I can write this. And we have shown that in the previous questions and in the classroom. And then just solve it. Point 0.5 meter cube rigid tank contains refrigerant at initially 160 kilopascal and 40%. We write it down. Heat is transferred now to the rigid tank, and the pressure becomes 700. Determine the mass of the refrigerant and the amount of heat transferred. Okay, and you can also show the process on a PV diagram. All right, so and the saturation lines are argon. Okay, and then let's take a look at it. Initially we have a mixture, so we are somewhere here, mixture, and then we're gonna have we don't know what gonna have, so we might wanna as well draw this part later on. But we know that we have a mixture for now at initially, because they give us the quality. So let's take a look at it. First of all, how we can determine the mass. There is one way, like if you know a volume, which we know, and if we can figure out specific volume at the first state, we can use that, because mass is volume times specific volume at first state or second state. But in this case, for first state, it is easier because we are given the quality and the pressure. So what we can do that is first figure out the first state conditions. From there, we need to figure out what is the specific volume or other properties we might need. So this is at 160 kilopascal. We are told that we have a mixture. So the only way to find this is using quality and this equation. And of course, you can do that. You can look at the tables at 160 kilopascal, but this time for the refrigerant, right? We go to tables, and at 160 kilopascal, right there, we previously highlighted this, we can read what is VF, what is VG, what is UF, what is UFG, whatever we need, we can read from there and then calculate the properties that we want. And then okay, the next thing is the second state. The next thing is we were trying to calculate the mass, right? We can calculate the mass. And this is 10.03 kilogram. Okay, and we found the mass. The next thing they're asking for is the amount of heat transferred. So the only way to find it is writing energy balance, and from there we can figure it out. The only energy interaction is heat getting in, changing the internal energy of our system. Therefore, we need to know the mass and internal energies, specific internal energies. We know the mass now, but we need to calculate also for the first state what is U1, and we can do that. From quality. Okay, that's the answer. And then the next thing is second state. Second state is they give us the pressure, and we are not given anything else, but from the knowing that we have a rigid tank, specific volumes has to be the same, and therefore specific volume was this, right? 0.0497887. And this should lead us to the right tables to read what would be the second state internal energy. And let's take a look at it at 700 kilopascal. And what is the V value we have? 0.049, which is about this. So you have a superheated, and then we go 0.7. I feel like as if something we did this already or something. Okay, and then we need to figure out the specific internal energy. This is question we did already, so that's very good. So I think we did this question already, and let me check which question was it. And this question already also done 2 times, but let me check. 0.5. Okay, there we go. We already did this. And I explained to you that you need to extrapolate. Okay, very good. So we just need to get the answer from there. But in more detail, they're explained how we do extrapolate. You guys can listen to that too. So you find this to be all right. And with that being said, if we look at the heat equation, heat is getting in and change the internal energy, right? We need to write down the mass and U2 minus U1, which should give you 2708 kilojoule. That's the answer. One thing is we might want to go back and sketch this diagram, PV diagram, because we know we have a mixture and then we have superheated here. And of course, from mixture to superheated at the constant volume, this has to be like this, and the dome should be like this, because under the dome we have a mixture, and then we have superheated, which is happening at the constant volume. So there is a rigid tank, contains a mixture of water and vapor, liquid water and vapor at 100 degrees Celsius with a quality 12.3. The mixture is heated until its pressure is 150. Calculate the heat transferred required. And only way to do this is write the energy balance. Energy getting in minus the energy getting out, changing the internal energy. The only energy getting in is heat. There is no energy getting out, and we find it using this equation. And now that means I need to know the mass, I need to know the internal energies, and similar to previous example, we can do that. First of all, analyze state 1, mixture, percent. I'm sorry, we need to divide 200 this one, because quality has to have a volume between 1 and 0. Okay, so this is it. We know mixture, we know quality, it's the temperature, and then we should be able to calculate from table A, let's say A4 first, because it is the water at 100 degrees Celsius. Find table A4, 100 degrees Celsius. What is the VF, VFG, or UF, UFG? Oh, this is VG, VF, and UF and UFG. So we can know those, and we can write it down and also use it in our calculations. So from here, I'm just gonna use what we just read to calculate these values. That's wrong. So here we write down how we calculate the values for specific volume and internal energy at first state. looking at the tables, Vf and Vg minus Vf. Okay, so and then for the internal energy, we can do the same thing. Now for the second state, we are given the temperature, which is 150. And also we know that this is a rigid tank and specific volume should be the same. Let's take a look at 150 degrees Celsius. What is Vf and Vg? And our number, our value is in between those, right? 0.2066, and in between those. So that means you have a mixture, and if you have a mixture, now the first thing is therefore remembering is that we need to find the quality. And we can do it using specific volume. Vf is 0.001091. And then we find this. Okay, so from there we need to again calculate the internal energy. And UF is this. Okay, so the last thing is left for us is put those into the equation of energy balance and calculate the heat interaction, because heat is equal to mass times and the mass was we calculated Did we? Oh, we didn't. We can do that too. So how we can calculate the mass? Let's do it here in this region where we have a mass calculated from volume over specific volume, and the volume was initially 10 liters, so meaning 0.1 meter cube. So let's use that here. Approximately 47 kilojoule. So a fixed mass of saturated water vapor at 400 kilopascal is isothermally cooled until it's a saturated liquid. Calculate the amount of heat rejected. So there's a cooling, and this cooling is causing our water to become a liquid from a vapor. From a saturated vapor, it becomes a saturated liquid. And if you remember the property diagrams, this can happen only when there is a phase change at a constant pressure and at a constant temperature. So what I would do is, first of all, they are not telling us if this is a piston cylinder device or a rigid tank. So that is tricky because we need to know. And I think in that sense, this problem statement is not very clear. And if we assume that there is no boundary work here, there is no piston cylinder device and it's a rigid tank, we can solve it in that way. We can also solve it if it is a piston cylinder device. So assuming this is a rigid tank, and what is happening is heat is getting out and from our system, which is causing a change in the internal energy. So if we look at the energy balance, the only energy interaction is heat getting out. This is 0, and it is changing the internal energy. Now with that information, we should be able to find the heat rejected from the internal energies. Let's try it. So first state they are giving, it's 400 kilopascal, and they are telling us that it is saturated vapor. So if we look at the tables, it's the water at 400 kilopascal. Right, this line, and we are trying to find the internal energy for saturated vapor. That means we are reading actually the UG, right? UG. Okay, making sure we are at the water table, and 400 kilopascal, we can read that value that I just show for 400. And of course this was U1. For U2 it is a saturated liquid, but it's isothermally. So how are we gonna figure this out? We have saturated liquid, and at that temperature, which must be the saturation temperature, right? The temperature has to be 143.61, and at that temperature you should also be at that pressure for the phase change to happen. So if we go back to the temperature table, so 143 should give you again around 400 kilopascal for the saturation pressure. But this is U2 is simply the UF at that pressure. So we go and UF is 604.22. Now you know U2, U1, and but you don't know the mass, so it is very difficult here. First of all, that you need to figure out the mass, but the key here is to catch the word. That if you notice, you need to figure out the mass, but you are not able to, not even think information is given, that if you read it carefully, it actually asks you heat rejected per unit mass, meaning if you simplify your equation by dividing each term to mass, what you have is gonna be heat getting out per unit mass. So all you need to do is subtract the internal energies. So the heat getting out is therefore per unit mass is this. Now, if it is a rigid tank, then you need to include the boundary work. In this case, boundary work has to be compression. Why? Because the volume is getting smaller. Because you had a vapor, it is becoming a liquid. So it is compression. So in your energy balance, you need to include boundary work getting in minus the heat getting out is causing a change, right? And in that case, is it easy to solve? We need to check, because this can be found from PDV, which is a constant pressure process. And so we might need to divide each term to mass. We can do that. So this will give us P delta B specific. And next you need to do and so we already found this part. This is similar to what we done, and the pressure is constant 400 because there is a phase change, and pressure and temperature should stay the same. And the volume change, and now for the volume change you will have to figure out the volumes, right? So for example, specific volume has to be Ug at the first state, and it has to be Vf at the second state at that pressure. And then you can plug in the volumes here and calculate that, and that is also possible, but the problem statement should clearly tell us whether it's a rigid tank or whether it's a piston cylinder device, so that we know how to include the boundary work or not. Alright, there is a piston cylinder device that contains steam initially at 1 megapascal and 450 degrees Celsius and 2.5 meter cubed. So we would sketch it first. Steam is cooled at a constant pressure until it first starts condensing. So the point it starts condensing from steam, the first it starts is when it becomes a superheated, saturated vapor, right? Because remember the diagram. We have superheated in this region, and the first point that it starts condensing is when we have a saturated vapor. So that means that first we had steam, but then at second state we have a saturated vapor. Okay, now very good. So we actually graph the PTV diagram here, because initially we have superheated and now we have saturated vapor, and this is our dome saturation lines, and here is from first state to second. So now we get the whole picture, and now they're asking mass of the steam. Immediately I realized they gave me volume. If I know the specific volume, I can able to calculate it. So that means I need to figure out the specific volume, which I can, because they give me pressure and temperature. I can look at the tables. So at 1000 kilopascal, the temperature for saturation is 179.88, and we are much above that. That means we have superheated. And for the superheated, if you go to superheated tables at 1 megapascal, you can see directly they don't have 450, so that means you need to interpolate to find the temperatures. So do the interpolations and you will find specific volume is okay. Let's do that later. And after that, this is the first part, right? They were asking for TV diagram. We need to find the mass of the steam first, or in the mass of our system in this piston cylinder device. And if you do that correct, it should give you this. And this is the first part. Now the second part is they're asking for, so we did this part, they're asking for the final temperature. For finding the temperature of our system, we need to look at the tables. And for second state, we know the pressure, and because it's a constant pressure process, and we also know, I'm sorry, yes, we also know that it's a saturated vapor. So from the same tables, here, since at that pressure we have saturated vapor, you can see that temperature has to be 179.9. Okay, so that part we also did. And now the amount of heat transfer. And the only way to find the amount of heat transfer if we use the energy balance. And here, of course, you can see that there is, this is how I would do it. Okay, so basically we don't know if it's compression or expansion, and from the graph of TV diagram I would say the specific volume is getting smaller, right? So I would say there is I would expect to have some volume change, which is volume decrease, which is a compression. So what I would do is write energy balance. And what energies are getting in, therefore, is boundary work and heat changing the internal energy. Okay, so from here you can then say how we can calculate the boundary work from PdV, and how we can calculate the heat. That is what we are trying to find out. And this is M times. Well, now you need to go back and figure out the specific volumes we already did for both states and internal energies for both states. So if you do the interpolation at the first state, you should find U1 you should find from UG and UVG the second state. Properties. Now after you figure this out, plug in the numbers. So we don't have space left. We're gonna go to the next page. So P delta V minus Q out was equal to M delta U. Okay, in other words, okay, let's check it's correct. Okay, so here what are we going to do? We are trying to find for heat, right? So we know the pressure. Let's write it down. We know the mass, that was 7.565. Specific volume at the second state, minus the specific volume at the first state, minus mass times internal energy change should give you the heat that is getting out. And the answer should be this. An insulated piston cylinder device contains 5 liters of saturated liquid water at a constant pressure of 175 kilopascal. Okay, and the volume is, okay, so water is steered by a paddle wheel. Shaft work getting in, while a current of 8 ampere flows for the 5 minutes through a resistor. Electric work is getting in. So half of the liquid is evaporated during this constant pressure process. It says half of it is evaporated, means basically you start with a saturated liquid, then it becomes a mixture, and half of it is evaporated. So the quality is 0.5. Okay, so what is given is this, and the paddle wheel work amounts to 400 kilojoule. Determine the voltage of the source. And we might have done this somewhere in our class problems. It sounds like it. And but let's solve it again. Okay, so first of all, what are they asking for is the voltage, and I need to find electric work to find the voltage. So what I need to do is write the energy balance. Energy getting in minus energy getting out is changing the energy of our system. So in this case, shaft work is getting in, electric work is getting in, but boundaries work is getting out because it is expanding from a saturated liquid to a mixture. Oh, I'm sorry, we said boundary. That is changing the internal energy. Now, in this case, when there is a boundary work out and internal energy change, here on the right hand side at a constant pressure, we can combine them. Remember and write it as enthalpy change. And in this case, we are given this one. We need to find this. So we need to find the enthalpy change, which from property tables, we should be able to do that. Because they are giving you the pressure is 175 kilopascal, and they are telling you it's a saturated liquid, and you can check the tables for H1. And also specific volume is something you need to check to calculate the mass. Okay, and the next thing is we need to find mass and H2. For H2, the pressure is, second state pressure is the same. And then you also know the quality. You can do your calculations to figure out what H2 is, because you need to use quality at that pressure to calculate the second state specific enthalpy. And if you do that, you should get for H2 this volume. Now, with that givens, we also need to figure out the mass. Mass is volume over specific volume. And we know the volume. They are giving this. We know the specific volume. And the mass is okay. And we know the mass, we know the enthalpies. Now I can find electric work. Let's do that. Shaft work is 400. We are trying to find electric work, which is equal to mass times enthalpy change. Okay, I'm gonna continue in the new page. Okay. So we figured out that our electric work should be this volume. Now electric work is given to us with an equation, and let's first of all check everything is correct. Yes, and given to us with an equation voltage times ampere times voltage times current times time. Okay, but we need to use a unity conversion ratio here, don't forget, because we need to convert that voltage times ampere term to kilojoule per second. So this is how we do it. This is our unity conversion ratio. The current is 8, I think, and then time is in terms of seconds. And this should tell you that actually your voltage is 223.9. Okay. Okay, so a temperature of 2 kilograms of neon is increased from 20 to 180. Calculate the change in the internal energy. And if this would change if we have an argon instead of neon. Of course, it would change because it's a different substance. And for neon and argon, those gases, we don't have a exact table that gives us CV and CP as a function of temperature. The main reason for that, those gases might not be changing their value of CP and CV to a large extent as a function of temperature. So only table we have is at 300 Kelvin. What is the volume of Cp and Cv for neon and argon? And we need to read Cv because we are trying to calculate internal energy. And these values. Well, these are the values we can use for 300 Kelvin. And within a wide range of temperature changes, probably these gases do not significantly change their specific volumes, that we don't have tables for those gases other than these. So what we can do is only use the values for Cv that are given to us in table A2A. I think that was it. Table A2A. Let me check it. Yes. And we can use that. So basically what we are trying to say here is they're asking for the internal energy change, and that is we calculate for an ideal gas when we can replace delta U with Cv delta T. And we need to accept a single Cv value between those temperature ranges, and then mass is 2 kilogram, and we read the Cv to be this value, and the temperature change is this. Okay, so with that, if you do the calculations, you should find this to be 197.7 kilojoule. If you repeat the same for, this is for neon, and then if you repeat the same process, which is 2 kilogram times 0.3122, you will find 99.9 kilojoule for argon. So of course it has changed. Why? Because the volume of Cv is changed. That's why, for different gases. Similar to previous example, in this case they're asking for the enthalpy change for argon and neon, and this time there's a temperature change from 75 to 25. And we use the same table. This time we're gonna read Cp values. The reason for that is they're asking for enthalpy change, and enthalpy change is calculated using Cp. Remember, enthalpy change, they're asking in kilojoule per kilogram. That's why it is Cp delta T. So if we do this for argon, reading the Cp values, actually the other way around, because it is dropping temperature. So the temperature at the second state is 25. So it is decreasing the enthalpy. And if this is for the argon, we can repeat it for the neon in the same way. The Cp is just gonna change. That's it. This time we are dealing with internal energy change of hydrogen gas in kilojoule per kilogram, and the temperature is changing from 200 to 800, and they're asking for us, let's calculate it from the average temperature and also from the room temperature value of CV. And since they gave us the temperatures 200, you can average them, and this is 500, and we go to table A to B for the hydrogen column. 500 CV is 10.389. We go back for this average temperature. CV average is excellent. Now we can calculate internal energy change in kilojoule per kilogram, because it is just CV delta T. Horrible writing. Okay, that's it. Now they're asking, what if we use the room temperature CV, which is at 300 Kelvin, that you can look at it, which is 10.183. I think you can also check for that in this table. That's it. Now this time for nitrogen, we do the same, but we are calculating enthalpy change, and enthalpy change is related to CP, not CV. Therefore, we need to read CP values for nitrogen. For the average temperature of 600 plus 1000 over 2, 800. So for 800, we need to use CP, 1.121. Now we can repeat it for the room temperature value, which is this one. And this will give you that. An insulated rigid tank is divided to two equal parts by partition. Initially, one side contains 4 kilograms of an ideal gas. The other part is evacuated. Now it removed. The whole tank is filled with the gas. Determine the final temperature and pressure. Now this is an ideal gas problem, and therefore I need to use ideal gas equations if I need to find the temperature and the pressure of the tank. basically. And the volume is doubling. And also we need to remember that because it is divided into two equal parts. Basically, P1 V1 over T1 is equal to P2 V2 over T2. So we know P1. If we say V for the initial volume, T1 is 50 plus 273. Pressure is something they're asking for, and they're also asking for the temperature, right? So this is 2V. So in this case, I'm seeing that we have two unknowns, and this will not give me directly. That means there has to be a way that I figure out the temperature at the second state. So how can I do that? And the way to do it is actually look at the energy balance. So energy getting in minus energy getting out is creating a change in the internal energy. Now, there is no energy interactions here. First of all, this is insulated. No heat is getting in or out, or no boundary work because the boundary is not moving. The boundary is the one that I sketched. So there is no boundary work, there is no heat interaction, there is no energy transfer. So your internal energy change actually has to be zero. So what does that mean is, since mass cannot be zero, they are giving 4 kilogram. That means U2 minus U1 is 0. What means is these are equal to each other. Since these are equal to each other, that means temperatures has to be equal to each other. So you actually know second state temperature, which is the same. With that being said, we cancel out the temperatures and the volumes, and that means you have 800 kilopascal over 2, which should be giving you the second state pressure, which is 400 kilopascal. So the temperature is the same and the pressure is 400 kilopascal. An insulated piston cylinder device contains 100 liters of air at 400 kilopascal and 25 degrees Celsius. Immediately I noticed there are no heat interactions, I'm sorry, because it's insulated. But this is a piston cylinder device, there can be boundary work, and initially the volume is 100 liter. And then the pressure and the temperature is given. Since this is an ideal gas, probably we will use ideal gas equations. So in terms of Kelvin, this is 298. So a paddle wheel is rotated. There's shaft work getting in. Until 15 kilojoule of work done on the air. Okay, so I guess this means that they are giving us the shaft work, right? And while the pressure is held constant, determine the final temperature of air, neglect the energy stored in the paddle wheel. Okay, so basically this is ideal gas question, and also we need to write energy balance to figure out certain properties. And how we can do that, let's see. So there's energy getting in, and that must be pushing the piston and causing it to do some boundary work out. So if I want to write energy balance here, that is gonna be the shaft work getting in minus the boundary work getting out is equal to the change in the internal energy. But as you can remember, if we have a constant pressure process, we can combine these and write them in terms of enthalpy change. If you go back to listen to other problems, this is similar to that. And so very good. We know 15 kilojoule of paddle work is done, and what happens is if we know the first state enthalpy mass, I can calculate H2, and if I can calculate H2, I will be able to calculate the temperature. Since this is air, I can look at table A17 if I know the specific enthalpy at the second state. So mass should be easy to find because this is an ideal gas problem. So mass is equal to P1 V1 over RT1. We found the mass. The next thing is H1. We can find it because they are giving me the temperature. So I can look at table A17 to figure out H1. And you do that from table A17. So let me do this way. Okay, so we have 290. Okay, so we read that volume, and from this equation we're gonna calculate the second state enthalpy. This is 15 kilojoule getting in, changing the enthalpy. And you find H2 to be this. And now you need to go back to tables and find at that temperature what is your enthalpy. You might have to do interpolation there to write the exact numbers. I'm sorry, the enthalpy is given to us, right? Enthalpy is 320.23, so we might need to do some interpolation, and to figure out the temperature is actually very close to 330, but it is 329.9 Kelvin. Okay, I think this is it. Let me check. They just ask for the temperature, right? That's it. In this question, again, we have air, and there is piston cylinder device which has a paddle wheel. Initially, it is 400 kilopascal and 17 degrees Celsius. Paddle wheel is turned on by an electric motor until 75 kilojoule per kilogram work has been transferred to air. Okay, so it is the amount of the shaft work basically. And then during this process, heat is transferred to maintain a constant air temperature while allowing the gas volume to triple. Well, they give a lot of information here actually. And calculate the amount of heat transfer. So the only way to calculate the amount of heat transfer is if we write down the energy balance. So basically energy is being transferred, shaft work is getting in, heat is getting in. That should be pushing the piston out. And therefore, if we look at the energies that are getting in, these are the energies that are getting in, and the boundary work is getting out because this is a piston cylinder device, changing the internal energy of the system. Now, is this a constant pressure process? We don't know. We know that this is a constant temperature process, but we don't know if it's a constant pressure process. So I won't be able to sum up delta U with the boundary work and say this is enthalpy change. But what I know is something that is very valuable, which is they tell me there is no temperature change. So if there is no temperature change for an ideal gas, that means its internal energy is not changing, because delta U is for an ideal gas mCV delta T. But this is 0 in this situation. That means there is no internal energy change. Whatever the energy we put in is pushing the piston. That's it. And the internal energy is not changing. So they're asking for the heat transfer though. So if I want to calculate the heat transfer getting in, I will have to calculate the boundary work and subtract the shaft work. Now, shaft work is known. They say 75 kilojoule per kilogram. So we are talking about mass per unit mass, heat transfer or work per unit mass. Okay, what we can do is, that means basically on a per unit mass basis, if you divide each term to mass here, it will make our energy balance this way. So they already give it this one to us, 75 kilojoule per kilogram. Now I need to figure out this one and how I can do it. Now you need to remember this equation. Right? And this is not a constant pressure process, this is a constant temperature process. So the mass replaced with the pressure replaced with MRT, which gets out of the integral, and we need to MRT over V, and it gets out of the integral this way for a constant temperature process. Remember, this is so we integrate that, and this is our answer. Now, we don't know the, let's see if we know actually the ratio of the volumes, which is helpful because it is tripling, right? So basically this volume is ln, this is like ln 3 because V2 is 3V. It's like this because it triples, and we know that part. And for MRT, since I am normalizing these equations with mass, only thing I need to know is MR term there, and I'm sorry, the RT term. So because I'm dividing all these to mass, right? Which I don't need to know the mass to begin with, so I don't have to deal with that part. And they are not giving that to me, and I don't have to calculate it in any way. So all I have to do is to calculate boundary work per unit mass that is getting out is RT ln 3. So R and T we can figure it out because R is 0. Temperature is 17 degrees Celsius is 290 Kelvin, and then that is ln 3. Okay, so if you do that, this is gonna give you 91.4 kilojoule per kilogram, and it is the work output per unit mass. Now this doesn't end our calculations because I need to go back and look at the heat, how I can calculate the heat. This one, right? So I can do that if I subtract Okay, so there was a fire alarm in the building, so I had to get out of the building, but now we continue where we stopped. So here the boundary work out per unit mass, we figure it out. Now the next thing is put it in our energy balance. That's the answer. And here at the final question, we have air with a mass of 15 kilogram. It's piston cylinder device, and they are giving us temperature change from 20 to 77. And there's a current passing through, which is providing electric work, electric energy to the system. And the pressure inside the cylinder is constant, 300 kilopascal, but there's a heat loss of 60 kilojoule. Determine the electric energy supplied. So the only way to do this is, of course, we need to write the energy balance, okay? So first of all, we know the energy getting in minus the energy getting out is creating a change, and energy is getting in here is electric, and that's it. What is getting out is heat and boundary work. Now it's tricky here to understand if boundary work is getting in and or out, but if and I would suspect here is that first of all, of course, the question should clearly signify and let you know that it's getting in or out by telling you how the volume changes, because then you understand is if it's a compression or if there's boundary work getting out. Now here they say the system is being heated, so the internal energy is changing. Okay, so this signifies to me if the energy is changing, increasing inside due to these energy interactions, then even though of course the heat is getting out, there is electric work getting in. So in essence, in some of these, so basically altogether these energy transfers, energy interactions, causing your system's internal energy to increase because its temperature is changing. That means its internal energy is changing, and that should push the piston, and you should have a boundary work out. That is what I would suspect to happen. And then in this constant pressure process, there is also the advantage where we can combine these two terms and write in terms of enthalpy change. Now, we are asked to calculate electric work. So all we have to do, therefore, find the enthalpy change and add heat interaction. They already give us heat interaction is 60 kilojoules. And all we have to do is here find the enthalpy change. And we can do that from m times so how do we find H1 and H2? If this is an air and if I know the temperatures, which I know here because they say 20 to 77, I should look at table A17 for each temperature, find the corresponding enthalpy. And if you do that, you will be able to calculate the enthalpy change These are from table A17 that you figure out. Units all make sense. All of them are this kilojoule. And then this should give you electric work of okay. Now here though they say find it in terms of kilowatt hours. So that means you might need to use a unity conversion ratio here that you can utilize to do that conversion. One kilowatt hours is equal to 3,3600